Hola, React Alicante. Me llamo Mateus y estoy muy encantado de estar aquí con vosotros hoy. Woo! But that's all the Spanish I got for now. Sorry. So yeah, today we're here to talk about fibers and a lot about internals of React, because yeah, we're here for React, right? Yeah, this is me. You can find me everywhere as Y Combinator. I'm a senior software engineer at Medallia. You probably saw us around here. And also I mentor front-end at Tech Labs. So before we start, I do have a couple of disclaimers. So the first thing is we're going to be talking about the source of React, and it's something that changes a lot over time, and sometimes it's even confusing. So some of the thoughts you're going to see here are speculations. And the second thing is at some points, we'll notice a lot of it's going to sound a lot like in depth. So just check, if you're lost, just check for this emoji, and that means, yeah, we're going to have discussions after this session. So a bit of the whys and the context and why we're here discussing this. My story with that started back in 2020 when a friend of mine, he was working on a Bubble plugin because he was preparing a TC39 proposal and he wanted to add algebraic effects into JavaScript. So he prepared a plugin for that and he asked me for feedback. And when I was going through that, I saw this huge cloud of terms and words, expressions, etc. Some of them I had never heard. So I saw algebraic effects, continuations, coroutines, etc. But at the same time, I didn't have a lot of idea about them. I had heard of them before in React, especially fibers. So that was when I had the idea for this, to put them all together in a way that it makes sense into the world of React, and that we can see how they all piece together in that. So starting with fibers, one of my favorite ways to start thinking about fibers is as stack frames. So let's see, we have this very, very simple piece of JavaScript. It's a function that adds two numbers, as you figured. And so we declare it and then we evoke it with 2 and 2. If we were to have a stack frame for that in JavaScript, we could start modeling with something like we have the return, we have the function itself, we got the couple parameters, and we have local variables. In this case, the local variable is result. If we were to trace something like a parallel into the world of React for a component, we could have this structure that we're going to call a fiber, and we would have something similar. We would have a return. Instead of the function, we would have our component, which a lot of times happens to be a function. Instead of parameters, we have props, and instead of the local variables, we have a local state within the component, for example. So in React, this thing of fiber architecture is this React-specific implementation of a call stack alike model. It's not necessarily a call stack, but it looks like one that basically allows React to have full control of scheduling what should be done. And we're going to talk a lot about this word scheduling. And a fiber itself is, we can think of then as a stack frame for a given React component. So we talk a lot about work. So we can start thinking of fibers as units of work. So let's recap what happens in React. First, we have our templates, our JSX stuff. It goes through the compiler, and we have a lot of React elements. The things in the past we saw, like React.create element. And then we have the so popular reconciliation. So the data that is returned from all of these elements, the render method of them is merged into a tree of fiber nodes. And the data structure that they came up with that was really impressive, by the way. And of course, depending on the type of the element, React under the hood needs to perform different stuff. So if that is a class function, it's going to do some work. If that's a function component, it's going to do something. If that's a portal or a suspense component, so on and so on. And then each element is converted into this fiber node that is going to describe exactly what React needs to do. So that's why we can think of them as units of work. And the fact that they are really good abstraction for units of work is what makes them convenient for tracking, scheduling, pausing, aborting, and like doing anything with work. Okay, now that we can abstract them as units of work, we can also think about visualizing them like that. And for this, we have the first experiment. So let's inspect elements. We have a very simple app. It's got a local state, and I'm incrementing, decrementing, and like I have a component to render that. If we start inspecting the fibers of each of those elements, we're gonna find a lot of metadata, including props, state, next props, next state, what's memoized, what's not. And yeah, I know it's hard to read. I don't expect you to. It's more like so that you see how much data we have inside one element. And we can do things with the data, for example. So in this code, we have a very simple JavaScript map, and we are iterating through the fiber nodes we have in the app. And we are getting some specific information, like the siblings, the child, and stuff like that. And we are attaching that to our JavaScript map. So let's see how that works with an example app. So Twitter uses React. So I've literally copied and pasted the code into developer tools. And now I'm going to inspect one button. Yeah, I created the map. I should have probably zoomed a bit more. But yeah, I just clicked the button so that I have it as the current element in DevTools, and now I can access that with fibersmap.get and then that current element, and I can see, for example, all the metadata. Oh, yeah, I refreshed, but I can see all the metadata about that one element. So, and we can figure out that, for example, Twitter has more than 4,000 class components. And it's really interesting when we start digging into the source, because, for example, we find a lot of stuff into the source of reconciler. So this is the part of the code, for example, where we can see what each field of a fiber is. And we have interesting stuff like the word tags. So basically, these are tags that mark each kind of work that React has to do. And this is a very interesting thing to see the evolution of the framework, because every year I check that the number changes. So last time I checked it was 25. So you can see like stuff like off-screen components, context components, suspense, profiler, all these things. Okay, now that we know that they are units of work and that we can visualize them, we can also start manipulating them. So for this, we're going to have another exercise. But before, who here has heard of this weird word, homogeneity? Okay, a few. So for this, I have an example in Clojure. It might sound a weird language, but don't worry. This code is actually quite simple. What we're doing here is we are binding x to the value of 1. And then after that, we increment to have like 2. And the thing about this code in Clojure is that it can be thought as a list of 3 elements. So we got a symbol that is the let, we got a vector with 2 elements, and we got an array with 2 elements. And we can expand these 2. So this first vector has got a symbol that is x and an integer. And the second thing, we got a symbol that is increment and another symbol that is x. And why I'm showing Clojure, basically because I wanted to get to this concept. I got it from Wikipedia. And homogeneity is this property of programming languages in which the code used to express the program is written using the data structures of that language. So it's like as you're coding, you're basically handling the AST of the language itself. And what does it have to do with React? Because we just saw that React elements are just data. So just like we would do in Lisp or any other Lisp-like language, our components can be used to manipulate their children and return something else. And this takes us to the second experiment, that is pattern matching in React. So I'm going to do the raise your hands things again. So who has heard of pattern matching? I guess this is more popular. Yeah, cool. Quite a few. Anyways, I had to add a definition. So pattern matching basically consists of specifying patterns to which some data should conform and then checking to see if it does, and just deconstruct the data according to those patterns. So just a few languages, they have this really, really strong with them. Haskell is one of them. So if we were to write factorial in Haskell, we would have this. So we define first the base case that is 0, and then it equals to 1, and then we recursively define it using matching patterns. And we can get to scenarios where we have more patterns, like in Fibonacci. For example, here we have an extra pattern, so we are matching for 0, we are matching for 1, and then we match the general case. And why is that? Because this can be really handy in React. So here's a piece of code where basically I have a hook. Let's say it's doing some async stuff, an API call or whatever. And here I got a couple components, match, with, and otherwise. And what I'm doing is I'm matching against the shape of what I got in my hook. So if I got an error from the API, I'm going to render my fallback component. But if I got like an OK response and it was like a text, I can then like render this text. And if it was an image, I can render the image. And this is really powerful because we can have all sorts of predicates and type safety and etc. And the whole thing with homogeneity and etc. is because the code is all, it works under the hood by inspecting the type of these elements and using utilities from React like children.toArray to go through the elements. And this kind of thing enables us to do some really powerful stuff. So we can combine that with suspense and dynamic imports. And we can, for example, have pattern matching with suspense and lazy, and our users would only download the bundle of a component that matches a given shape. So that's really amazing. And again, all of that based on reflecting on elements data. If you're interested, you can check out, I kind of turned this into a lib, but it's not production ready. Just use it, just check it out. And one of the last things about fibers is that they're not just a React thing, actually. This idea is not new. And basically, fibers are this generic model of execution in a comparative way. And we can even see fibers in some operating systems or in some other languages, like OCaml, we got fibers like in the language itself. Now we can move to coroutines. Are you all good? I started checking out coroutines because of this tweet by Andrew Clark. He's one of the core committers of React for a couple years now. And he said that suspense would trick people into learning about coroutines. So he was right. And I started trying to find definitions for these. And the first one I saw was that a coroutine is a generator or a producer, if you will, that can also consume values. So I was like, okay, JavaScript generators, they can consume values. So by this definition, they could be coroutines. Another definition out there is that it's a generator that can resolve async values, like we have with async-await. And that's another really common definition in the JavaScript world, especially because who here has been doing JavaScript before we had promises? Like, yeah, quite a few. So you remember, for example, we had Co or Bluebird utilities for doing promises before they were part of the spec or when they were still being drafted. Or even Bubble under the hood, it was doing generators to implement async-await. So that's another quite popular definition of coroutines. And last but not least, we find the most fancy one, that is, it's a generator that can yield with a stackful continuation. And we'll talk about that. But for now, we can imagine as if we had a async-await at different depths. And this is kind of, we can see inspiration in Suspense, for example, because Suspense, we can pause the reconciliation of React at any depth. So it could be it. So recapping a bit before we move forward, in Fibers, we have control passed to a scheduler, in this case, the scheduler of React. And this scheduler is going to determine what's going to be run next. And this is controlled at the level of framework or operating system, be it whatever. It could be event loop and node. And in coroutines, we have control passed to the caller, and it's handled by your code, by application code. So what does it have to do with React? So it all started a couple years ago when they were actually trying to make a new built-in component, just like we have nowadays suspense profile, etc. So it was a specific component type Actually two. We had coroutine component and uid component. And the idea back then, as opposed to suspense, was to give the components explicit control over using and resumption of the whole thing. And by the way, this is the same file that we saw in the beginning, where we have a full list of the possible component types. And it's a really interesting discussion, actually, to check it out. But this didn't move forward because they had a couple issues trying to optimize that and especially memorize that. But I admit it's going to be fascinating to see at some point in time they resume any kind of this of work. But it's not because it doesn't exist anymore that we cannot explore them. So we can try to see coroutines in concurrent React, for example. So this is a really good session by Dan Abramoff a couple years ago when he was going through time slicing and like concurrent React for CPU bound operations and network bound operations. And he was basically showing how to optimize a lot of things with time slicing, like CPU heavy stuff. And I'd like to create a similar scenario here. So again, we have an app. And as I'm typing, you can see that I virtually made this input CPU bound. So you can see that it's kind of blocking the main thread. So it gets to a point that I need to wait until I can type more. And the experience starts to get poorer. And then Chrome crashes and so on and so on. And the code for that is basically this. So we have this resourceful component. And it's calling this resourceful operation. And the heavy stuff I'm doing is I'm iterating up to 1 million. And you might think I wouldn't iterate up to 1 million a component, but it would do other stuff like heavy data processing. So how could we improve that? And now for this, we have yet another experiment. So who here has used Redux sagas? Cool. Wow, quite a few. So yeah, Redux Saga was like one of the most popular middlewares, I would say, for Redux. And it was really amazing, I gotta say. And it had like really, really good ideas. And one of them was the usage that they had of generators. So they were using ESX generators, for example, to do parallelization, concurrency, and other stuff like handling haste conditions and that kind of stuff. And I think we can get some inspiration from Saga for this one example. So how about we do this? And what happened is, first, we made that resourceful operation a generator. And the reason why we did that is just that I want to yield execution back to the event loop right in the beginning of its call. And now I have two things. I have this scheduler object that I'm creating, and then I call perform unit of work. So let's see what happens. Yeah, first you can see that it's suspending. So the user is aware that there's some heavy stuff going on. And the second thing is that the input is responsive all the time. So it's not like quite a poor user experience like the one before. And this is the full code for the whole scheduler object. But we can focus in this part that is perform units of work. And what we're doing here is basically we are switching against 3 different states. So we have idle, pending, and done. And the magic, besides throwing promises for suspense, is that we are using the next method of our iterator coming from our generator. And using that, we can, for example, yield or not. So if you see that, it might sound a lot like we just used something like use transition from React 18. So if we go back for the original example and try to rewrite that with transitions from React 18, you will see that, yeah, we just did something similar. But instead of using React scheduler, we used our own scheduler that we created in 40 lines with coroutines. So back to coroutines and scheduling in React. What we have in React is a cooperative multitasking model. So we don't have WebAssembly, we don't have workers, we don't have anything like that for parallelism. What we have is a single thread for rendering that is interruptible. So because of that, rendering can be interleaved with other work in the main thread, including other work from the browser and other React renders, for example. And because of that, an update can happen in the background without blocking the response to new input. So that's what's happening in concurrent React. And it's better if we visualize. So this was the example. We had the original render task. Then I started typing. So we had user input. Because it's user input, it is high priority. So React starts doing that. And then it's smart enough to resume as soon as it has handled the input. So there's a lot of magic stuff under the hood going on here, but one of my favorite ones is React yields the execution back to the main thread every 5 milliseconds. And I know it sounds a lot like a magic number, like the ones we use in CSS, but it's not. It's because it's smaller than a single frame, even when you have 120 FPS. So because of that, it doesn't block animations. And because of that, in practice, it's interruptible. Another thing amazing about coroutines is to see their usage out there. And for this, we can talk a little bit more about asynchronism in JavaScript. So asynchronicity in JavaScript is what we call contagious. So for example, and you've probably been there, when you're migrating something from a callback-based API or something like that, and you start doing promises, and then you start with async await, then you have more and more awaits, and then you have to go all up your code modifying that. So that's it. If any function is async, anything that calls it must also be async. And so on until your entire code has async await everywhere. And I'm not saying it's necessarily a bad thing. But the thing is, the synchronicity isn't free. So it does, just like almost everything else, it does have overhead. And the thing is, every async function we have, it has to first allocate callbacks and store them somewhere. But also, it has to take a trip back to the event loop before invoking those callbacks. And we have a really interesting case to see this overhead, SASS. So, SASS? Yeah. I was like, I need to do this. Yeah, so probably a lot of you are using SASS. So let's talk about asynchrony in SASS. The SASS API, it has two main methods for compiling SASS files. It's got the sync and the async version. And over time, the async version became more and more used because it was better, for example, for Webpack, for building Webpack plugins, loaders, and it was like kind of what's going on in the community. Everyone was doing async stuff. And the thing is, for Node SASS, you couldn't tell like a difference because everything in the end was running on C++. But the thing is, for Dart SASS, because it was running in the end as pure JavaScript, it was also subject to the JavaScript rules and limitations of asynchronicity. And what happened in the end is not only the async version was slower, but it was like 2 to 3 times slower than the sync version. And to address that, they started using Node fibers under the hood to implement the async version with the sync fast code. So this is Node fibers, and yeah, for years it was one of my favorite libraries out there. And unfortunately, it got deprecated last year because of some changes in the core of V8 and Node. But the point is, we can see usage of fibers and coroutines like in other parts of our ecosystems. And because we did quickly mention continuations, we can also address them, but this one's going to be a quick one. So I first saw continuations, again, in some PRs in the core of React. And then when you start digging about that, you see definitions like it's an abstraction that represents the remaining steps in the computation. But we can assume as a continuation as a control flow primitive, just like we had if, else, and loops. So it's a control flow primitive. And there are interesting discussions around the React ecosystem for continuations. And we have some parts of the reconciliation inspired by continuations, one of them being the perform work function. It's not like exactly like this in the source of React, but this is like a simpler version. But what's happening here is this function, it handles a queue of tasks in a while loop, just like the one we had in our demo. And what happens is, if there's still anything in the queue, it returns the perform work, and schedule it for resumption after some later time. That React has a lot of heuristics to determine that. And in this context, this thing represents a continuation of a queue of tasks. And continuations are around there on the web as well. So they're part of the main thread scheduling API that is being prepared for the browser. And we even have examples of using that, for example, with yield and is input pending and other experimental APIs of this whole thing. I would definitely recommend that you check it out. But let's go to the last part, that are effect handlers. Whew. So when we start digging about effect handlers, we find a lot of abstract stuff. I mean, they sound abstract for us. So we see that they are this thing that asks the environment, the call environment, to handle one task. And when an effect is used, the nearest handler is called, which allows you to run the nearest code in response to that effect. And I know it's really hard to visualize that, but luckily Dan Abramov wrote a post about that a couple years ago that is algebraic effects for the rest of us. And actually effects are something present in other languages like F or some functional programming languages. And in his post, Dan linked this example. It's not JavaScript, it's like a dialect of JavaScript that he mimicked just for the code. But what we can see here, he's basically doing as he had like some async thing that would return array start. And what we see here is these blocks like perform, handle, and resume. And if we think a bit, it sounds a lot like throw, try, catch. But instead of throw, we have perform. Instead of catching, we are handling effects. And this resume with thing is our continuation that lets us jump back to where we performed the effect. And you might think, why was Dan Abramov talking about that, and what does it? Oh, why I am here talking about that? So we can see the influence of effect handlers throughout the history of React. First, with the layout algorithm. So a couple of years ago, they were experimenting with data structures based on effect handlers for managing layout in React applications. And again, really interesting discussions. And then we all know the context API. So when they were redoing it for React 16.3, again, they experimented that for the context API, and they even remodeled the context API based on effect handlers. It didn't move forward, again, because of problems trying to optimize that. But again, also really interesting discussions. Fast forward time, we have other members of the core team experimenting with it for handling side effects within a component. And this is a piece of code by Sebastian Mockbach, another guy from the core team. And we can kind of see the same pattern here. So, but instead of throw, back then years ago, he used raise. And instead of catch, he came up with catch effect syntax proposal. But again, we can see this pattern of different members in different years trying to come up with something like that. And then we have hooks. So when they were coming up with the drafts for the hooks API, again, hooks were heavily inspired by effect handlers. And Sebastian even points that by definition, hooks could be abstracted as algebraic effect handlers. And last but not least, what happens to be my favorite thing in React and algebraic effects, let's see something. So who here has built a suspense ready API? Like not used, but built something that supports suspense. Yeah, okay, a lot doesn't help a lot. So here are a couple of examples. This one is one library by Daishi. No, actually, this is React Fire. And in the documentation, you can see that there are concurrent React features. You can see that React Fire hooks throw promises that suspense can catch. And if we start checking the source code of suspense compatible libraries, you're going to see something like this. So this is another library, and we're going to see promises being thrown away. And even if we check the source of React Cache, that is a project that's been on for a while now, we're going to see something like this. So we can see that in suspense, a component is able to suspend the fiber it is running in by throwing a promise, and this promise is caught and handled by React under the hood. And if I were to say, the first thing I think of when I see that is the same throw, handle, resume pattern that we saw in effect handlers, but without effect handlers because JavaScript doesn't have them. Whew. So a couple of closing notes and things I think we can learn from all that. The first is, I think that React Fiber, it's not like a thing, but first, React Fiber was a rewrite of React focused on giving more low-level control over execution. And we have fibers as this cooperative way to model execution in low level, and we have algebraic effects and continuations and etc. as a way to handle effects where these and their behavior are independent. The second thing we can notice is that React strongly tries to address the lack of some JavaScript features or language level resources or even resources in the browser by implementing their own alternative solutions. So, for example, the first time I see, oh, they're throwing promises, like what a hacky solution, I could do that. But the thing is, it's basically a way of coming up in an environment and in a language where we don't have that. And the same thing with continuations and etc. And not only this, but we can see that these solutions, they kind of help the web moving forward. And that's one of the reasons why the scheduler API quickly showed React core team is one of the main teams cooperating in that. Another thing that we can see is that understanding these internals and the motivations behind them, because, okay, you might know, oh, they're firm promises, but why? So understanding the why behind them can help us implement our own abstractions, our own stuff. So we saw two examples, the coroutines-based scheduler and the pair matching for components. That pair matching thing, for example, it helped me a lot in a scenario where I had to implement different behavior across different browsers, depending on objects or depending on predicates and that kind of stuff. Another thing is that for the next one, I've got the quote by Guillermo, the CEO of Verso. You probably know him. So he said in 2016 that React is such a good idea that we would spend the rest of the decade exploring its implications and applications. And I couldn't agree more. I think that it's easy for us to see how React has been pushing not only the web, but also other ecosystems forward. I come from iOS, so I saw, for example, Swift UI happening and other things like ResSwift and Reactive Cocoa and other stuff that were not only you could see, but they were by documentation inspired from what was happening back then with React, Flux, Redux, etc. So I want to say that the fact that we're here in Alicante discussing all of these topics that are, I mean, they're not common in the front-end realm. It's not like we are discussing about compilers and features of the languages and things like this as front-end developers on a daily basis. So I think that the fact that we are here doing this shows that React is this democratic agent for this kind of knowledge in the front-end world. And I think that's another implication of what Guillermo said. You know what they say? That a picture is worth 1,000 words. So for my next conclusion, I got a picture. This is me 8 years ago. And I was telling iOS developers that Ionic and Angular would be the future. I even had the Angular swag back then. So, yeah. It took a while, but maybe another closing thought is don't always trust all my speculations and future predictions. And I'm glad you started clapping at this time because we are hiring massively, including here in Spain. So yeah, you're supposed to clap now. So yeah, if you want to work with us and Medallia, do amazing stuff with performance and other stuff that's interesting, just this QR code, find us at the booth. We got swag, we got a lot of things. Um, the slides for this session are gonna be they are available right now on my speaker deck. So I'll try not to skip for 10 seconds because I always skip the slide before people can actually take a photo of the most important QR code. If you like that kind of stuff, like sessions about programming languages, internals, performance optimization, and that kind of stuff, I have other sessions. So this is the go-to link for anything about Medallia and other sessions. It's probably the most important thing to emphasize that I got stickers. So yeah, if you want stickers, let's reach out. And if you have questions or if you want to share your experience about React performance, that kind of stuff, let's hang out. And that's all I had for today. Muchas gracias.